Hello everyone, in today's class we're going to go through the energy balance in heat transfer. So if there's two types of energy balance. There's one that can be done on the control volume, which is the system, and there's one that can be done on a small section of the system, which is the control surface. It's done on the surface of the control volume. So we'll start with the first one. Okay, energy balance on a control volume. So let's assume this to be our control volume. Okay, this here is our control surface. Let's assume that we have energy flowing into our control volume and energy leaving the control volume. If the energy going in is more than the energy coming out, that means there's some energy accumulated inside the volume that's being left inside, and that's the energy stored. If, for example, in our system we have energy being generated, then we have to take into account the energy generated inside the system. Okay, so let's identify each of these variables we wrote down. En is the rate of energy entering the system. Okay, this dot here symbolizes rate, meaning that the energy is going in per time. So energy usually has the units of joules, but since that dot is there, that means the rate of energy going in, it's energy per time, which is joules per second, which can also be written as watts. Now, E out is also the rate of energy leaving the system. Okay, energy generated is the rate of energy generated inside the system, and energy stored is the rate of energy stored inside the system, or the energy accumulated that's left inside the system and haven't left. Okay, so the energy balance of a control system will basically be the energy entering the system minus the energy leaving the system plus any energy that's being generated inside the system will equal the energy stored inside. That is energy balance for a control volume. Energy balance for a control volume. Okay, now let's look at a surface. So a surface means this small part of the control volume. So if we take it out and magnify on that small part, kind of expand it a little just to see what's going on. So this here is our control volume. This dashed line is the control surface. Now, the thickness of our surface is negligible. It's so small it approaches zero. Therefore, we'll assume the volume of the surface, which is the thickness, is zero. It's very negligible. It approaches zero. We assume it to be zero. Therefore, if the volume is zero, we know that mass equals density times volume. So if volume is zero, mass also is zero or approaches zero. Okay? Now, if the mass is zero, we know that the energy stored will equal to mc Cp delta T. So if mass is 0, the energy stored itself will be 0. Also, if mass is 0, there won't be any, if the mass is 0 or the volume is 0, there won't be any area or place for energy to be generated. Therefore, energy generated is also 0. So, if we write down the energy balance of a control volume that we found on top, which is energy in minus energy out plus energy being generated equals the rate of energy stored, automatically we can cancel these two terms, because when dealing with a surface, these two terms do not exist. Therefore, the energy in will be left with energy in equals energy leaving. And that is the energy balance of a control surface. Okay, so let's go ahead and look at an example. Okay, let's look at this example here. A thin electrical heating element provides a uniform heat flux to the bottom of a rectangular duct. So this rectangular duct here, air enters, just give me a sec, the air enters through the duct, and there's a heating element right at the bottom. So the cool air, or the normal air temperature, ambient air temperature that enters the duct, is being heated by the heating element at the bottom. Therefore, the warm air enters the room and heats up the room. So if we take a look at it from another angle, this here is the bottom of the duct. So this is the heating element right there, and this is the duct wall at the bottom, which is 10 millimeters thick. And on top here is the air that's flowing, the ambient air that's flowing to be heated. Okay, now we're given the thermal conductivity, the convection coefficient, the surrounding temperature, and Ti, which is the surface temperature of the duct wall. Now they're asking us to find the initial heat flux that the heater is producing. So I want you to pause the video, try to solve it yourself, and then resume the video and see how I solved it. Okay, these are the givens. So let's go ahead and start. So we need to start with an energy balance. So let's count down the unknowns that we don't have. One is the heat flux that's required. 2 is the surface temperature of the heater. Okay, so let's start with an energy balance. We can perform an energy balance at any point. There's no right or wrong answer. We can perform a control volume energy balance, a control surface energy balance, the top surface, the bottom surface. It really depends on what you want. All of these equations are dependent, so you'll get the same result. So what I'll do is I'll start with a control volume energy balance, meaning that I'll take the energy balance of the entire system. Okay, so if this is the duct wall, right, this is the heating element. Now, we're assuming the heating element to be perfectly insulated, meaning that there's no energy that escapes to the bottom. Okay? The only energy goes upwards into the duct wall. So this is our initial heat flux. So a controlled volume of the entire system will look like this. So whatever is going into that system has to leave at the top. Okay, but since the top is being exposed to a fluid, which is air, therefore the heat flux on the top is convection. Therefore, we can say that, hey, the heat flux entering the system from the bottom, which is from the heating element, has to equal the heat flux leaving out, which is in convection. Now we know heat flux of convection will equal to H Ts minus T infinity. Ts is the Ti, which is the temperature of the duct wall surface, the surface temperature of the duct wall on the top. Okay, now we can enter these numbers which are given. Okay, T infinity, therefore the initial heat flux equals 100 watts per meter squared Kelvin times 85. As I said again, this is our Ti, temperature of the surface on the top of the duct, which is 85 Celsius minus 30 Celsius. The reason why these two are in Celsius and they won't affect this Kelvin here is because they are difference of temperature. So if they were in Kelvins, they'll have the same difference in temperature as if they were in Celsius. Okay, so it won't really affect the final answer. It won't affect the final answer at all, to be honest. So the initial heat flux will equal to 5,500 watts per meter squared. Okay. Now we need another energy balance to find the TO, which is the temperature, surface temperature, the initial temperature of the heating element, or the surface temperature of the heating element. So to do that, we need to perform a control surface energy balance. Okay. So let's now draw our schematic of the problem. So we have two options. We can perform a surface balance, energy balance on the top or on the bottom. Both are correct. Okay. Let's try the bottom. Okay. They're both correct. I can do both and show you that both of them give you the same answer. Okay, let's try the bottom. That's the heating element. This is your initial heat flux that's entering into the wall. Now, if we pick the bottom, we'll say, hey, the energy, the heat flux going into the bottom surface has to equal the heat flux leaving the bottom surface. Okay? And the heat flux leaving the bottom surface is conduction. Why? Because there's a metal surface there. Okay? There's no fluid, there's no air. Therefore, the initial heat flux will equal to the conduction heat flux. Therefore, that will equal to K delta T over L. You know, this is 10 millimeters. Okay, K is given to be 20 watt per meter Kelvin. So the initial heat flux will equal to 20 watt per meter Kelvin times delta T, which is TO, this here, minus TI, right there. Okay, let's make this a little smaller. TO minus TI divided by the change in the thickness of the wall, which is 10 millimeters, which is 0.01 meter. These are in Celsius. Okay, this is 85 Celsius and this is unknown. We can plug our initial heat flux that we found from the above energy balance, watt per meter squared, equals 20 watt per meter Kelvin, make sure the units match, times TO, which is unknown, minus 85 Celsius divided by 0.01 meters. Therefore, TO will equals to 87.8 Celsius. Okay, now if you did a top surface energy balance, it's also correct, and I can show you. Okay, so this is the schematic of the duct wall. We're using the surface here for our energy balance. We know that the heat flux entering that surface is conduction. Heat flux leaving that surface is convection. Therefore, conduction heat flux equals to convection heat flux. That'll be K delta T over L equals H Ts minus T infinity. Okay, K is 20 times TO minus TI over L, 0.01 meters, equals to H, which is 100, times Ts, temperature of your surface here. The convection surface is Ti, which is 85 Celsius. 85 minus 30, which is the temperature of air. This here is 85. Okay, and you'll get the same answer. TO equals 87.8 Celsius. So again, there's no right way to solve it. If you do your energy balance correctly, you'll end up getting the same answer, the same final answer, no matter how you do your energy balance. But since you have two unknowns, you need at least two equations to solve the problem. You need at least two energy balances. And that's it for this class. We went through energy balance and heat transfer, and see you in the next one.